Today, the topic that we are discussing is on the design of heat exchangers by using Ntu method or number of transfer units method, or it is also called effectiveness method. The heat exchangers can be designed by two methods: logarithmic mean temperature difference method or Ntu method. Logarithmic mean temperature difference method is applicable only when all the temperatures at the inlet of the heat exchangers and at the outlet of the heat exchangers are known. If the temperatures at the inlet of the heat exchanger and at the outlet of the heat exchangers are to be determined, then we will make use of Ntu method. Ntu method or effectiveness method. Before we go for the derivation on Ntu method, we need to understand what is meant by effectiveness of an heat exchanger. Effectiveness of an heat exchanger is defined as the ratio of actual heat transfer to the maximum possible heat transfer in an heat exchanger. In an heat exchanger, the hot fluid releases heat to the cold fluid and its temperature drops from Th1 to Th2. At the same time, cold fluid absorbs heat from the hot fluid and its temperature rises from Tc1 to Tc2. If the heat losses to the surroundings are neglected, then all the heat which is released by the hot fluid is absorbed by the cold fluid. Therefore, the actual heat transfer that takes place between the hot fluid and the cold fluid is given by the equation C suffix H into Th1 minus Th2 or C suffix C into Tc2 minus Tc1. C suffix H into Th1 minus Th2 gives the heat lost by the hot fluid, and C suffix C into Tc2 minus Tc1 gives the heat gained by the cold fluid, where C suffix H and C suffix C are heat capacities of hot fluid and cold fluid respectively. Heat capacity is nothing but the amount of heat required to rise the temperature of any fluid through 1 degree Celsius, or it is the amount of heat required to raise the temperature of the fluid. Now, if in an heat exchanger, if the length of the heat exchanger is increased to infinity, the temperature of the hot fluid can be reduced from Th1 to Tc1, and at the simultaneously the temperature of the cold fluid can be raised from Tc1 to Th1 if the length of the heat exchanger is increased to infinity. But this maximum change in temperature depends on heat capacities of the hot and cold fluid, and hence this maximum change in temperature can be attained by only one fluid. Therefore, the maximum allowable possible heat transfer in an heat exchanger is given by the equation C suffix H into Th1 minus Tc1 if the hot fluid is having minimum heat capacity. If the cold fluid is having the minimum heat capacity, then the maximum possible heat transfer in an heat exchanger is given by the equation C suffix C into Th1 minus Tc1. In general, the maximum possible heat transfer in an heat exchanger is given by the equation C minimum into Th1 minus Tc. Therefore, the effectiveness of an heat exchanger is given by the equation C suffix h into Th1 minus Th2 divided by C minimum into Th1 minus Tc1, or C suffix c into Tc2 minus Tc1 divided by C minimum into Th1 minus Tc1. We discussed on effectiveness of heat exchanger. The next topic that we are discussing is the design of heat exchanger, or the derivation of heat exchanger using Ntu method, number of transfer units method, for a parallel flow heat exchanger. A parallel flow heat exchanger is one in which both the hot fluid and the cold fluid flows in same direction. The hot fluid releases heat and the cold fluid absorbs heat. The temperature of the hot fluid drops from Th1 to Th2 and the temperature of cold fluid rises from Tc1 to Tc2. In a parallel flow heat exchanger, the temperature difference θ1 at the inlet of the heat exchanger is Th1 minus Tc1, and the temperature difference at the outlet of the heat exchanger is Th2 minus Tc2. θ2 value is Th2 minus θ2. The assumptions which we considered for LMTD method are same for Ntu method also. The assumptions that are made are, the first assumption is the specific heats of both the fluids remains constant and flow conditions are steady. Mass flow rate of the fluid remains same. These are the assumptions that we made for logarithmic mean temperature difference method. These assumptions remains the same even for Ntu method. Now we are discussing on the design of heat exchangers for a parallel flow heat exchanger using Ntu method. First, let us consider an elementary area dA of heat exchanger. dA of heat exchanger. We considered a smaller amount of area dA of the heat exchanger. The rate of heat which is exchanging between the hot fluid and the cold fluid through this elementary area is given by dq equals u into dA into Th minus Tc, where T suffix h is the temperature of the hot fluid in that elementary area at the inlet of the elementary area. We considered a small elementary area, and Tc is the temperature of the cold fluid at the inlet of the elementary area. Temperature of the cold fluid at the inlet of the elementary area. U is the overall heat transfer coefficient and dA is the small elementary area. As a result of heat transfer through this elementary area dA of the heat exchanger, the hot fluid is cooled by a small temperature dH. Its temperature drops by a small amount dH, whereas the temperature of the cold fluid rises by a small amount dT suffix C in the direction of heat transfer. The energy balance equation for this elementary area dA may be written as dq equals minus m into h into cph into dth equals mc into cpc into dtc, where mh into cph into dth gives the heat released by the hot fluid. Since the hot fluid loses its, we use negative sign for the hot fluid in the direction of heat transfer. Since the cold fluid absorbs heat, its temperature increases in the direction of heat transfer, we are using positive sign for the cold fluid. And these two equations can be equaled with u into dA into Th minus Tc. Call this as equation number 1. mH into Cph can be replaced by C suffix H, which gives the heat capacity of the hot fluid, and mc into cpc can be replaced by the term C suffix C, which gives heat capacity of the cold fluid. Therefore, we can write from the above equations dq equals C suffix h into dth equals C suffix c into dtc equals u into dA into Th minus Tc. Call this as equation number 2. From the equation number 2, we can write dt suffix c equals dq by cc and dth equals minus dq by ch. Subtracting these two terms, we will get dth minus dtc equals, taking dq term outside, minus dq term outside, we will get on the right side minus dq into 1 by ch plus 1 by cc. From equation number 1, we can replace dq with u into dA into Th minus Tc. U into dA into Th minus Tc. But from the figure, Th minus Tc is theta, the temperature difference at the inlet of the elementary area, and dth minus dtc can be written as d theta. Rearranging the terms, we will get d theta by theta equals minus u into dA into 1 by ch plus 1 by cc. Integrating this equation, we will get ln theta 2 by theta 1 equals minus u into a into 1 by ch plus 1 by cc, because the integration of 1 by x is ln x. Between the limits 1 and 2, we will get ln theta 2 by theta 1, and integration of x is, integration of dx is x. Here the integration of dA is a. Therefore, we will get the term ln theta 2 by theta 1 equals minus u into a into 1 by ch plus 1 by cc. Now substituting the values of theta 2 and theta 1. Theta 2 is the temperature difference at the outlet of the heat exchanger, which is equal to Th2 minus Tc2, and theta 1 is the temperature difference at the inlet of the heat exchanger, which is Th1 minus Tc1. And applying the anti-log term, when the ln shifts to right side, it becomes e to the power of minus e to the power. Applying the ln anti-log on both sides, we will get Th2 minus Tc2 by Th1 minus Tc1 equals e to the power of minus ua into 1 by ch plus 1 by cc. Call this as equation number 5. Now from the definition of effectiveness for the hot fluid, we are having effectiveness equals CH by C minimum into TH1 minus TH2 divided by TH1 minus TC1. Rearranging this equation, we will get TH2 equals TH1 minus effectiveness into C minimum by C suffix H into TH1 minus TC1. Call this as equation number 6. Similarly, for effectiveness, we are having one more equation, which is C suffix C into TC2 minus TC1 divided by C minimum into TH1 minus TC1. Rearranging that equation, we will get TC2 equals TC1 plus effectiveness into C minimum by C suffix C into TH1 minus TC1. Call this as equation number 6. Equation number 6 minus 7. By subtracting the equation number 6 with 7, we will get TH2 minus TC2 equals TH1 minus TC1 minus effectiveness into C minimum into TH1 minus TC1 into 1 by CH plus 1 by CC. On the right side, we are having TH1 minus TC1 common. Take the term outside, we will get TH2 minus TC2 equals TH1 minus TC1 into 1 minus effectiveness into C minimum into 1 by CH plus 1 by CC. From equation number 5 and 8, now substituting the value of TH2 minus TC2 in the equation number 5, we will get TH1 minus TC1 into 1 minus effectiveness into C minimum into 1 by CH plus 1 by CC divided by TH1 minus TC1 equals e to the power of minus UA into 1 by CH plus 1 by CC. TH1 minus TC1 get cancels, and we left with 1 minus effectiveness into C minimum into 1 by CH plus 1 by CC equals e to the power of minus U into A into 1 by CH plus 1 by CC. Rearranging this equation, we will get 1 minus e to the power of minus UA into 1 by CH plus 1 by CC equals effectiveness into C minimum into 1 by CH plus 1 by CC. Therefore, we will get the equation for effectiveness as 1 minus e to the power of minus UA into 1 by CH plus 1 by CC divided by C minimum into 1 by CH plus 1 by CC. Now, in the above equation, if we consider, let us consider for the sake of simplicity, for the sake of designing the heat exchanger, let us consider the heat capacity of the cold fluid as minimum. It may be hot fluid or the cold fluid, but for the sake of derivation, we are considering cold fluid is having the minimum heat capacity. Then we will get effectiveness equals, from the equation number 9, we will get 1 minus e to the power of minus UA. We considered C suffix C as the minimum heat exchanger, means is having the minimum heat capacity, and we have taken that outside. Then we will get effectiveness equals 1 minus e to the power of minus U into A divided by C minimum into CC by CH plus 1 divided by C suffix C into C suffix H plus 1 equals 1 minus e to the power of minus Ntu into c plus 1 divided by c plus 1, where Ntu equals u into a by c minimum, which is a constant, and c equals c minimum by c max, the capacity ratio. It is called the capacity ratio, and this is the final equation for effectiveness in case of parallel flow heat exchanger. For the equation for the effectiveness of a parallel flow heat exchanger is given by 1 minus e to the power of minus n into 1 plus c divided by 1 plus c. The value of effectiveness is maximum when the value of Ntu for the given value of c minimum and the c max is infinity. At that condition, the effectiveness equation becomes 1 by 1 plus c, because e to the power of minus infinity is nothing but 0. Next, we are deriving equation for counterflow heat exchanger for Ntu method. In Ntu method, a counterflow heat exchanger is one in which both cold fluid and the hot fluid flows in different direction. Here you can see the hot fluid is flowing from left to right, and the cold fluid is moving from right to left. In this case, the temperature difference at the inlet of the heat exchanger, at the left side of the heat exchanger, is Th1 minus Tc2. In case of parallel flow heat exchanger, it is Th1 minus Tc1. But here the theta 1 value is Th1 minus Tc2, and the theta 2 value at the outlet of the heat exchanger, at the right hand side of the heat exchanger, is Th2 minus Tc1. Don't get confused. For a parallel flow heat exchanger, it is Th1 minus Tc1, and for counter flow heat exchanger, it is Th1 minus Tc2. Similarly, on the right hand side, for a counter flow heat exchanger, it is Th2 minus Tc1. For a parallel flow heat exchanger, it is Th2 minus Tc2. This is the basic difference between a counter flow heat exchanger and a parallel flow heat exchanger. Similar to the parallel flow heat exchanger, here also let us consider a small elementary area dA of an heat exchanger. The transfer of heat, the exchange of heat through this elementary area dA can be given by the equation dq equals u into dA into Th minus Tc, or equals u into dA into delta T, where delta T is the temperature difference between the hot fluid and the cold fluid, Th minus Tc, Th minus Tc. As a result of heat transfer through this elementary area dA of the hot heat exchanger, the hot fluid is cooled by a temperature dTh, whereas the cold fluid is heated by a small amount by a small temperature dTc. The energy balance equation over the elementary area dA may be written as dq equals minus mh into cph into dTh equals minus mc into cpc into dTc, which is equal to u into dA into Th minus Tc. Here you can observe one thing. Here I am using the negative sign for both hot fluid and the cold fluid, because the temperature of both the hot fluid and the cold fluid is decreasing in the direction of heat exchanger, that is from left to right. Therefore, we are using the negative sign for both the hot fluid and the cold fluid. But in case of parallel flow heat exchanger, we used the negative sign for only one fluid. but here we are using for both the fluids. mH into Cph can be replaced by a term Ch, which gives heat capacity of the hot fluid, and Mc into Cpc can be replaced by a term called C suffix C, which gives the heat capacity of the cold fluid. Therefore, the dq equals minus Ch into dTh equals minus Cc into dTc equals U into dA into T suffix H minus Tc, called as the equation number 2. We can write from the equation number 2, we can write dTc equals minus dq by C suffix C, and dTh equals minus dq by, and we can write dTh equals minus dTc. The subtracting the two terms, we can write dTh minus dTc equals minus dq into 1 by Ch minus 1 by Cc, taking that minus dq term outside. Now replacing the dq with the term with the equation U into dA into Th minus Tc, we can write dTh minus dTc equals minus U into dA into Th minus Tc into 1 by Ch minus 1 by Cc. But we know that Th minus Tc, the equation gives the temperature difference between the hot fluid and the cold fluid at the inlet of the elementary area, which can be replaced by the term theta, and dTh minus dTc can be replaced by the term d theta. We will get the equation d theta equals minus U into dA into T theta into 1 by Ch minus 1 by Cc. Call this as equation number 3. Now rearranging the equation, we will get d theta by theta equals minus U into dA into 1 by Ch minus 1 by Cc. Integrating the equation between the limits 1 and 2 on the left and right side, we will get 1 by integration of 1 by theta is ln theta. We will get ln theta 2 by theta 1 equals minus U into A, because the integration of dx is x and the integration of dA is A, minus U into A into 1 by Ch minus 1 by Cc. Call this as equation number 4. Ln theta. Rearranging the equations, this equation number 4 can be rearranged in the form ln theta 1 minus ln theta 1 divided by theta 2 equals minus U into A into 1 by Cc minus 1 by Ch. I have taken negative sign on both left and right side. Call this as equation number 5. Replace theta 1 by the terms Th1 minus Tc2, which is the temperature difference at the left hand side of the heat exchanger, and replace theta 2 by Th2 minus Tc1, which is the temperature difference on the right hand side of the heat exchanger. We will get Th1 minus Tc2 divided by Th2 minus Tc1 equals e to the power of minus U into A into 1 by Cc minus 1 by Ch. Call this as equation number 6. Now definition of effectiveness for an hot fluid, the effectiveness equal C suffix H into Th1 minus Th2 divided by C minimum into Th1 minus Tc1. Rearranging this equation, we will get Th2 equals Th1 minus effectiveness into C minimum by Ch into Th1 minus Tc1. Call this as equation number 7. The one more equation of effectiveness we are having is the C suffix C into Tc2 minus Tc1 divided by C minimum into Th1 minus Tc1. Rearranging this equation, we will get Tc2 equals Tc1 plus effectiveness into C minimum by Cc into Th1 minus Tc1. Call this as equation number 8. Now substitute this equation number 7 and 8 in equation number 6, which is th1 minus tc2 into th2 minus tc1 equals e to the power of minus ua into 1 by cc minus 1 by ch. We are substituting equation number 7 and 8 in this equation number 6. We will get th1 minus tc1. In the numerator we are substituting the value of tc2, and we will get th1 minus tc1 minus effectiveness into c minimum by cc into th1 minus tc1, and in the numerator we are substituting the value of th2, and we will get th1 minus effectiveness into c minimum by ch into th1 minus tc1 equals e to the power of minus ua into 1 by cc minus 1 by ch. On the left hand side, in the both in the numerator and denominator, we are having the common term is th1 minus tc1. Taking that term outside, we will get th1 minus tc1 into 1 minus effectiveness into c minimum by cc, and in the numerator we will get th1 minus tc1 into 1 minus effectiveness into c minimum by c suffix h. th1 minus tc1 get cancels. We will get 1 minus effectiveness into c minimum by cc in the numerator, and in the denominator we will get 1 minus effectiveness into c minimum by ch equals e to the power of minus ua into 1 by cc minus 1 by ch. Now cross multiplying the term e to the power of minus ua into 1 by cc minus 1 by ch with the denominator term, we will get 1 minus effectiveness into c minimum by cc equals e to the power of minus ua into 1 by cc minus 1 by ch minus effectiveness into c minimum by ch into e to the power of minus ua into 1 by cc minus 1 by ch. Now rearranging the above equation, we will get the equation for effectiveness as 1 minus e to the power of minus ua into 1 by cc minus 1 by ch divided by c minimum into 1 by cc minus 1 by ch into e to the power of minus ua into 1 by cc minus 1 by ch. Now let us consider the cold fluid, the heat capacity of the cold fluid as minimum, and taking that term outside, we will get 1 minus e to the power of minus ua by c minimum into 1 minus cc by ch divided by 1 minus cc by ch into e to the power of minus ua by c minimum into 1 minus cc by ch. Now replacing ua by c minimum with ntu or minus n. Ntu is equals to ua into c minimum, and replacing cc by ch means c minimum by c max with a term called cc, which is defined as the capacity ratio. We will get the equation for effectiveness as 1 minus e to the power of minus n into 1 minus c divided by 1 minus c into e to the power of minus n into 1 minus c, where NTU equals ua into c minimum and the c equals c minimum by c max, which is defined as the capacity ratio. For a given value of c minimum and c max, If the NTU value is infinity, then the effectiveness of counterflow heat exchanger becomes equal to 100%, because e to the power of minus infinity is 0 and e to the power of minus infinity is 0. 1 minus 0 by 1 minus 0, it becomes 1 by 1, and the effectiveness of heat exchanger is equals to 1 if the value of NTU is equal to infinity.